This is a reading of one of my articles, and you can find a link to the original in the description below. Name distributions as artifacts on confusing priors with models. Being Abraham de Moivre and being born in the 17th century must have been a really sad state of affairs. For one, you have the bubonic plague going on, but even worse for de Moivre, you don't have any computers or sensors for automated data collection. As someone interested in complex real-world processes in the 17th century, you must collect all your observations manually, or waste your tiny fortune on paying unreliable workers to collect it for you. This is made even more complicated by the whole dangerous to go outside because of the bubonic plague thing. As someone interested in chance and randomness even in the 17th century, you've got very few models of random to go by. Sampling uniform random variables is done by literally rolling dice or tossing a coin. Dice which are imperfectly crafted as not to be quite uniform, a die or a coin which limits the possibilities of your random variable between 2 and 20, most likely 12, but I'm not discounting the existence of medieval d20s. You can order custom dice. You can roll multiple dice and combine the results into a number. E.g., you can roll 4 d10s, and that's enough to sample a uniform random variable between 1 and 10,000. But it becomes increasingly tedious to generate large numbers. Even more horribly, once you tediously gather all this data, your analysis of it is limited to pen and paper. You are limited to 2 plotting dimensions, maybe 3 if you're a particularly good artist. Every time you want to visualize 100 samples a different way, you have to carefully draw a coordinate system and tediously draw 100 points. Every time you want to check if an equation fits your 100 samples, you must calculate the equation 100 times. And then you must compute the difference between the equation result and your sample, and then manually use those to compute your error function. I invite you to pick 2 random dice and start throwing them until you have a vague experimental proof of the CLT holding. And then think about the fact that de Moivre's day must have been spent doing these kind of things for hours on end. Below in the article, there is a 10-minute video of me throwing 2 dice and seeing what their sum ends up being, though I think they might be a slightly bit loaded considering how they fall, but who knows. So it's by no accident, misfortune, or ill thinking that de Moivre came up with the normal distribution, trademarked later by Gauss, and the central limit theorem, the CLT for short. A primitive precursor of the CLT is the idea that when 2 or more independent random variables are uniform on the same interval, their sum will be defined by a normal distribution, also known as a Gaussian distribution or a bell curve. This is really nice because a normal distribution is a relatively simple function of 2 variables, mean and variance. It gives de Moivre a very malleable mathematical abstraction. However, de Moivre's definition of the CLT was that when independent random variables, which needn't be uniform, are normalized to the same interval and then summed, this sum will tend towards the normal distribution. That is to say, some given normal distribution will be able to fit their sum fairly well. The obvious issue in this definition is the tend towards and the random and the more than 2. There is some relation between these in that the fewer ways there are for something to be random and the more of these variables one has, the closer the sum will be to a normal distribution. This can be formalized to further narrow down the types of random variables from which one can sample in order for the CLT to hold. Once the nature of the random number generators is known, the number of random variables and samples needed to get within a certain error range of the closest possible normal distribution can also be approximated fairly well. But that is sort of besides the point here. The purpose of the CLT was not to wax lyrically about idealized random processes, it was to be able to study the real world. The Mauver's father, a proud patriot surgeon, wants to prove the sparkling wines of Champagne have a fortifying effect upon the liver. However, doing autopsies is hard because people don't like having their family corpses desecrated, and also because there is a plague. Still, the good surgeon gets a sampling of liver from normal Frenchmen and from champagne drinking Frenchmen and measures their weight. Now, normally, he could sum up these weights and compare the difference, or look at the smallest and the largest weight from each set to figure out the difference between the extremes. But the samples are very small and might not be fully representative. Maybe, by chance, the heaviest champagne drinker liver was 2.5 kilograms, but the heaviest possible champagne drinker liver is up to 4 kilograms. Maybe the champagne drinker liver are overall heavier, but there's one extremely heavy liver in the control group. Well, armed with the normal distribution and the CLT, we say liver weight is probably a function of various underlying processes, and we can assume that these processes are fairly random. Since we can think of them as summing up to yield the total liver's weight, we can assume that these weights will fall onto a normal distribution. Thus, we can take a few observations about the weights. Here in the article, there's a list of numbers about normal Frenchman liver weights and champagne drinking Frenchman liver weights. And we can compute the mean and the standard deviation. And then we can plot the normal distribution of liver weight, champagne drinker in orange and normal in blue. This is displayed in a graph in the original article. It looks like two bell curves, one in blue and one in orange, with the orange one being further to the right on the x-axis, which indicates a higher mean for the liver weight. So, what's the maximum weight of a champagne drinker's liver? Well, by looking at the graph, we can see that it's 3.3 kilograms. What about a normal liver? Well, the graph tells us that it's actually around 2.8. Minimum weight is 0.7 kilograms for champagne drinkers and 0.05 kilograms for the control, though maybe it was confounded by babies that are unable to drink champagne. This is pending further investigation. But we can also ask questions like, for normal people, say the 9/10 of people, the ones that aren't at the extreme, what's the range of champagne drinking versus normal liver weight? Or questions like, given liver weight X, how certain are we that a person drank champagne? Or, given that I suspect my kid has a tiny liver, say 0.7 kilograms, will drinking champagne give him a 4 out of 5 chance of fortifying it to 1.1 kilograms? So the CLT seems amazing. At least it seems amazing until you take a look at the real world, where we can't determine the interval for which most processes will yield values. You can study the stock market from 2010 to 2019, see that the Dow daily change is between -3 and +4% and fairly random. Assume that the Dow price change is generated by a random function with values between -3 and 4%. And then March 2020 rolls around, and suddenly that function will yield -22%, and you are fucked. Most processes don't accumulate, but rather contribute in weird ways to yield their result. Growth rate of strawberries is a function of lumens and water. But if you assume that you can approximate the function as lumens times A plus water times B, you'll get some really weird situations where your strawberries die in very damp cellars or wither away in a desert. Most processes in the real world, especially processes that contribute to the same outcome, are interconnected. Ever wondered why nutritionists are seldom able to make any consistent or impactful claims about diet? Well, maybe it'll make more sense if you look at this diagram of metabolic pathways, link in post. In the real world, most processes that lead to shared outcomes are so interconnected, it's a Herculean task to even rescue the concept of causality. On a surface level, my intuitions tell me it's wrong to make such assumptions. The epistemically correct way to think about making inferences from data ought to be along the lines of A. You can use the data at your disposal, no more. B. If you want data, you can either collect more or find a causal mechanism, use it to extrapolate, prove that it's true at the edge cases by making truthful predictions, and then use that. C. If you want more data, you can extrapolate given that you know of a very similar dataset to back up your extrapolations. E.g., if we know the distribution of Englishmen liver sizes, we can assume that distribution of Frenchmen liver sizes might fit that shape. But this extrapolation is just a better than random hypothesis, to be scrutinized further based on the predictions stemming from it. Granted, your mileage may vary depending on your area of study, but no matter how laxly you interpret the above, there is a huge leap to be made from those rules to assuming that the CLT actually holds for real-world processes. But again, this is the 17th century. There are no computers, no fancy data collection apparatus. There's a play going on, and to be fair, loads of things, from the height of people to grape yield on a vine, seem to actually fit the normal distribution quite well. So the Moivre didn't even have a minute fraction of the options we have now. All things considered, I think he was rather ingenious to come up with this. But, lest we forget, the normal distribution came about as a tool in order to 1. reduce computation time in a world where people could only use pen and paper and their own mind. 2. Make up for lack of data in a world where data meant what one could see around him, plus a few dozen books with some tables attached to them. 3. Allow techniques that operate on functions to be applied to samples by abstracting those samples into a normal distribution. In other words, allow for continuous math to be applied to a discrete world. Artifacts that become idols. So, the CLT yields a type of distribution that we intuit is good for modeling a certain type of process and has a bunch of useful mathematical properties in a pre-computer world. We can take this idea either by tweaking the CLT or by throwing it away entirely and starting from scratch to create a bunch of similarly useful distributions. And by a bunch, I mean a really, really large bunch. Here there's a link to the Wikipedia page of a list of important distributions in statistics. For the purpose of this article, I'll refer to these as named distributions. They are distributions invented by various students of mathematics and science throughout history to tackle some problem they were confronting, which proved to be useful enough that they got adopted into the repertoire of commonly used tools. All of these distributions are selected based on two criteria. A. Their mathematical properties, things that allow statisticians to more easily manipulate them, both in terms of complexity of thinking required to formulate the manipulations and in terms of computation time. Again, remember, these distributions came about in the age of pen and paper and maybe some analog computers which were very expensive and slow to use. B. Their ability to model processes or characteristics of processes in the real world. Based on these two criteria, we get distribution like students T, the chi-square distribution, the F distribution, the Bernoulli distribution, and so on. However, when you split the criteria like so, it's fairly easy to see the inherent problem of name distribution. They are a confounded product between A. Mathematical models selected for their ease of use, and B. Priors about the underlying reality those mathematics are applied to. So take something like Pythagoras' theorem about square triangles. Hypotenuse squared equals to the squared sum of the two sides. But assume we are working with imperfect real-world objects. Our triangles are never ideal. A statistician might look at 100 triangular shapes with square angles and say, they seem to vary by at most this much from an ideal 90 degrees angle. Based on that, he could come up with a formula like hypotenuse squared equals the sum of the two sides squared plus or minus 0.05 times the maximum value between the two squares of the sides. This might indeed be a useful formula, at least if the observation of the statistician generalizes to all right angles that appear in the real world. But a theorem or a rule it is not. Not so under any mathematical system from Euclid to Russell. If the hypotenuse of a real-world square triangle proves to be usually within the bounds predicted by this formula, and the formula gives us a margin of error that doesn't inconvenience further calculations that we will plug the result into, then the formula may indeed be very useful. But it doesn't change the fact that to make a statement about kind of square triangles, we need to measure 3 of the parameters correctly. The formula is not a substitute for reality. It's just a simplification of reality when we have imperfect data. Nor should we lose the original theorem in favor of this one, because the original is actually making a true statement about a shared mathematical world, even if it's more limited in its applicability. We should remember that 0.05 times the maximum value between the squares of the two sides is an artifact stemming from the statistician's original measurements. It shouldn't become a holy number, never to change for any reason. If we agree this applied version of Pythagoras' theorem is indeed useful, then we should frequently measure right angles in the real world and figure out if this magic error has to be changed to something else. When we teach people the formula, we should draw attention to the difference. The left-hand side is Pythagoras' formula. The right-hand side is this artifact, which is kind of useful, but there's no property of our mathematics that exactly defines what a slightly off right angle triangle is, or that tells us that this kind of triangle should fit this rule all the time. The problem with named distributions is that one can't really point out the difference between mathematical truths and the priors within them. You can take the F distribution and say this exists because it's easy to plug it into a bunch of calculations and because it provides some useful priors about how the real world processes that it models behave. You can't really ask the question, how would the equation defining the F distribution change provided that those priors about the real world would change? To be more precise, we can ask the question, but the result would be fairly complicated, and the resulting distribution, let's call it f prime, might not hold the useful mathematical properties of the F distribution. So the whole point of changing the priors is lost, since the resulting mathematical apparatus, after the priors have been changed, does not have any of the desirable properties which made us use it in the first place. Are named distributions harmful? Hopefully, I've managed to get across the intuition for why I don't really like named distributions. They are very bad at separating between model and prior. But, on the other hand, any mathematical model we use to abstract the world will have a built-in prior. Want to use a regression? Well, that assumes the phenomena fits a straight line. Want to use a 2 billion parameter neural network? Well, that assumes the phenomenon fits a 2 billion parameter equation using some combinations of the finite set of operations provided by the network. For example, plus, minus, bigger than, equal, max, min, and average. From that perspective, the priors of any given name distribution are no different than the priors of any particular neural network, or decision tree, or support vector machine. However, they come to be harmful because people make assumptions about their priors being somewhat correct, while assuming that the priors of other statistical models are somewhat inferior. Say, for example, I randomly define a distribution G, and this distribution happens to be amazing at modeling people's IQ. I take 10 homogeneous groups and give them IQ tests. I then fit G on 50% of the results for each group, and then I see if this distribution correctly models the other 50%, and it works almost flawlessly. I go further, I validate G using k-fold cross-validation, and I get tremendous results no matter what folds I end up testing it on. Point is, I've run a series of tests that, to the best of our current understanding of event modeling, show that G is better at modeling IQ than the normal distribution. Well, one would assume I could then go ahead to the neurology/psychology/economics/sociology community and say, hey guys, I've got good news. You know how you've been using the normal distribution to model IQ all this time? Well, I've got this new distribution, G, that works much better for this specific data type. Here is the data I validated it on. We should run some more tests. And if they turn up positive, start using it instead of the normal distribution. In semi-idealized reality, this might well result in a coordination problem. That is to say, even assuming I was talking with mathematically apt people that understood the normal distribution not to be magic, they might say, look, your G distribution is indeed X% better than the normal distribution at modeling IQ. But I don't really think that X% is enough to actually affect any calculations. And it would mean scrapping or rewriting a lot of old papers, wasting our colleagues' times to spread this information, and trying to explain this new thing to journalists that at least kind of understand what the bell curve is. In actual reality, I'm afraid that the answer I might get is something like, what? This can't be true. You are either lying or you are misunderstanding statistics. All of my textbooks say that the standard distribution models IQ and is what should be used for modeling IQ. And there is even a thing I heard that's called the central limit theorem that proves this. It's right there in the title. It's a theorem. That means that it's true. Maybe the actual reaction lies somewhere between my two versions of the idealized real world, the one that still has coordination problems, and the last version of the real world I presented. It's rather hard to tell. If I were a sociologist, I'd suspect there is some standard set of reactions mu, and they vary by some standard reaction coefficient, sigma, and 68.2% of reactions fall within plus minus 1 sigma of mu, 95.4% within plus minus 2 sigma, 99.6% within plus minus 3 sigma, and the rest are not very relevant to publishing in journals which would benefit my tenure application, so they don't exist. Then I would go ahead and find some way to define the min and sigma such that this would hold true. Alas, I'm not a sociologist, so I only have empty empirical speculation about this hypothetical. Other than the possibility of misguided assumptions about the correctness of their built-in priors, is there anything else that might be harmful when using named distributions? I think they can also be dangerous because of their simplicity. That is, the lack of parameters that can be tuned when fitting them. Some people seem to think it's a downside to use complex models instead of simple ones when avoidable. But I can't help but think that these are the same people that say you shouldn't quote Wikipedia. On the other hand, simple models can often lead to a poor fit for the data. Ultimately, this will lead to shabby evaluations of the underlying process. For example, if you are evaluating a resulting poorly fit probability density function rather than the data itself. Even worse, it'll lead to making predictions using the poorly fit model and missing out on free information that your data has but your model is ignoring. Even worse, simple models might cause discarding of valid results. All our significance tests are based on very simplistic probability density functions, simply because their integrals had to be solved by hand and computed in each point by hand. Thus, complex models were impossible to use. Does this lead to discarding data that doesn't fit a simplistic probability density function? Since the standard significance tests might give weird results due to no fault of the underlying process, but rather because the gathered data is just unusual. To be honest, I don't know. I want to say that the answer here might be yes, or at least no, but that's simply because one can massage the phrasing of the problem in such a way as to stop this from happening. I've previously discussed the topic of treating neural networks as a mathematical abstraction for approximating any function. So they, or some other universal function estimator, could be used to generate distributions that perfectly fit the data they are supposed to model. If the data is best modeled by a normal distribution, the function estimator will generate something that behaves like a normal distribution. If we lack data, but have some good priors, we can build those priors into the structure and the loss of our function estimators. Thus, relying on these kind of complex models seems like a net positive. That's not to say you should start with a 1000 million parameter network and go from there, but rather you should start iteratively from the simplest possible model and keep adding parameters until you get a satisfactory fit. But that's mainly for ease of training, easy replicability, and efficiency. I don't think there's any particularly strong argument against using a 1000 million parameter model if trained properly. I don't think it would be in any way worse than a 2-parameter model, assuming similar performance on the training and testing data. I've written a bit more about this in If Wonderwalls Was a Neural Networks, so I won't be repeating that whole viewpoint here. In conclusion, I have a speculative impression that statistical thinking is hampered by worshipping various name distributions and building mathematical edifices around them. I'm at least half sure that some of those edifices actually help in situations where we lack the computing power to otherwise solve the problems they model. I am also fairly convinced that if you just scrapped the idea of using name distributions as a basis for modeling the world, you'd just get rid of most statistical theory altogether. I'm fairly convinced that distribution-focused thinking pigeonholes our models of the world and stops us from looking at interesting data and asking relevant questions. But I'm unsure those data and questions would be any more enlightening than whatever we are doing now. I think my complete position here is as follows. 1. Name distributions can be dangerous via the side effect of people not understanding the strong epistemic priors embedded in them. 2. It doesn't seem like using name distributions to fit a certain process is worse compared to using any other arbitrary model with equal accuracy on the validation dataset. 3. However, most name distributions are very simplistic models and probably can't accurately fit most real-world data or derivative information from that data, at least not very well. We have models that can account for more complexity without any clear disadvantages, so it's unclear to me why we wouldn't use those. 4. Name distributions are useful because they include certain useful priors about the underlying reality. However, they lack a way to adjust those priors, which seems like a bad enough thing to override this positive. 5. Name distributions might pigeonhole us into certain patterns of thinking and bias towards giving more importance to some data that they can fit. It's unclear to me how this affects us. My default assumption would be that it's a negative, as with most other arbitrary constraints that you can't escape. 6. Name distributions allow for the usage of certain mathematical abstractions with ease, but it's unclear to me whether or not this simplification of computations is needed under any circumstances. For example, it takes a few milliseconds to compute the p-value for any point on any arbitrary probability density function using Python. So we don't need to have p-value tables for specific significance tests and their associated null hypothesis distributions, even though this may have been very useful in the 50s. Epilogue. The clock tower strikes 12. Moonlight bursts into a room, finding Abraham de Moivre sitting at his desk. He's computing the mean and standard deviation for the heights of the 7 members of his household, wondering if this can be used as the basis for the normal distribution of all human height. The ongoing thunderstorm constitutes an ominous enough scenario that, when lightning strikes, a man in an aluminum suit from a retro 70s space pop music video appears. "Stop whatever you're doing," says the time traveler. Demoivre looks confused. Look, this Gaussian distribution stuff that you are doing, it seems great, but it's going to lead many scientists astray in the future. Gaussian! Look, it doesn't really matter. The thing is that a lot of areas of modern science have put a few distributions, including your standard distribution, on a bit of a pedestal. Researchers in medicine, psychology, sociology, and even some areas of chemistry and physics must assume that one out of a small set of distributions can model their PDF for anything that they study, or their papers will never get published. Not sure I'm following. Okay, let's put it like this. I know you have good reason to use this distribution now, but in the future, we'll have computers, machines that can do calculations and gather data billions of times faster than a human. So all of this abstraction, by then built into the very fiber of mathematics, will just be confounding to us. So then why not stop using it? Look, there's a thing called behavioral economics, but it hasn't been invented yet, so I'm not sure how to explain it. The gist of it is something like, once a standard is entrenched enough, everyone must conform to it, even if it's bad, because defectors will be seen as having something to hide. Okay, but what... The door swings open and Leibniz pops his head in. You mentioned that in the future there are machines that can do an infinite number of computations, correct? Yes, you could say that. Was our mathematic not involved in creating those machines? Say, the central limit theorem that my friend Demoivre is working on now. I guess so. The advent of molecular physics would not have been possible without the normal distribution. That was used to model the behavior of various particles, I think. So then, if the CLT had not existed, the knowledge of matter needed to construct your computation machines in the first place wouldn't have been. And presumably, you wouldn't have been here warning us about the CLT in the first place. You see, the invention of the CLT, whilst bringing with it some evil, is still the best possible turn of events that one could hope for, as we are, after all, living in the best of all possible worlds.